In information technology, a backup, or the process of backing up, refers to the copying and archiving of computer data so it may be used to restore the original after a data loss event. The verb form is to back up in 2 words, whereas the noun is backup. Backups have 2 distinct purposes. The primary purpose is to recover data after its loss, be it by data deletion or corruption. Data loss can be a common experience of computer users. A 2008 survey found that 66% of respondents had lost files on their home PC. The secondary purpose of backups is to recover data from an earlier time, according to a user-defined data retention policy, typically configured within a backup application for how long copies of data are required. Though backups represent a simple form of disaster recovery, and should be part of any disaster recovery plan, backups by themselves should not be considered a complete disaster recovery plan. One reason for this is that not all backup systems are able to reconstitute a computer system or other complex configuration, such as a computer cluster, Active Directory server, or database server by simply restoring data from a backup. Since a backup system contains at least one copy of all data considered worth saving, the data storage requirements can be significant. Organizing this storage space and managing the backup process can be a complicated undertaking. A data repository model may be used to provide structure to the storage. Nowadays, there are many different types of data storage devices that are useful for making backups. There are also many different ways in which these devices can be arranged to provide geographic redundancy, data security, and portability. Before data are sent to their storage locations, they are selected, extracted, and manipulated. Many different techniques have been developed to optimize the backup procedure. These include optimizations for dealing with open files and live data sources, as well as compression, encryption, and deduplication, among others. Every backup scheme should include dry runs that validate the reliability of the data being backed up. It is important to recognize the limitations and human factors involved in any backup scheme. Storage, the base of a backup system. Data repository models. Any backup strategy starts with a concept of a data repository. The backup data needs to be stored, and probably should be organized to a degree. The organization could be as simple as a sheet of paper with a list of all backup media and the dates they were produced. A more sophisticated setup could include a computerized index, catalog, or relational database. Different approaches have different advantages. Part of the model is the backup rotation scheme. Unstructured and unstructured repository may simply be a stack of or CDRs or DVDRs with minimal information about what was backed up and when. This is the easiest to implement, but probably the least likely to achieve a high level of recoverability as it lacks automation. Full-only system imaging. A repository of this type contains complete system images taken at one or more specific points in time. This technology is frequently used by computer technicians to record known good configurations. Imaging is generally more useful for deploying a standard configuration to many systems rather than as a tool for making ongoing backups of diverse systems. Incremental. An incremental style repository aims to make it more feasible to store backups from more points in time by organizing the data into increments of change between points in time. This eliminates the need to store duplicate copies of unchanged data. With full backups, a lot of the data will be unchanged from what has been backed up previously. Typically, a full backup is made on one occasion and serves as the reference point for an incremental backup set. After that, a number of incremental backups are made after successive time periods. Restoring the whole system to the date of the last incremental backup would require starting from the last full backup taken before the data loss, and then applying in turn each of the incremental backups since then. Additionally, some backup systems can reorganize the repository to synthesize full backups from a series of incrementals. Differential. Each differential backup saves the data that has changed since the last full backup. It has the advantage that only a maximum of 2 datasets are needed to restore the data. One disadvantage, compared to the incremental backup method, is that as time from the last full backup increases, so does the time to perform the differential backup. Restoring an entire system would require starting from the most recent full backup and then applying just the last differential backup since the last full backup. Note: vendors have standardized on the meaning of the terms incremental backup and differential backup. However, there have been cases where conflicting definitions of these terms have been used. The most relevant characteristic of an incremental backup is which reference point it uses to check for changes. By standard definition, a differential backup copies files that have been created or changed since the last full backup, regardless of whether any other differential backups have been made since then, whereas an incremental backup copies files that have been created or changed since the most recent backup of any type. Other variations of incremental backup include multi-level incrementals and incremental backups that compare parts of files instead of just the whole file. Reverse delta. A reverse delta type repository stores a recent mirror of the source data and a series of differences between the mirror in its current state and its previous states. A reverse delta backup will start with a normal full backup. After the full backup is performed, the system will periodically synchronize the full backup with the live copy, while storing the data necessary to reconstruct older versions. This can either be done using hard links, or using binary diffs. This system works particularly well for large, slowly changing datasets. Examples of programs that use this method are diff backup and time machine. Continuous data protection. Instead of scheduling periodic backups, the system immediately logs every change on the host system. This is generally done by saving byte or block level differences rather than file level differences. It differs from simple disk mirroring in that it enables a rollback of the log and thus restoration of old images of data. Storage media. Regardless of the repository model that is used, the data has to be stored on some data storage medium. Magnetic tape. Magnetic tape has long been the most commonly used medium for bulk data storage, backup, archiving, and interchange. Tape has typically had an order of magnitude better capacity-to-price ratio when compared to hard disk, but recently the ratios for tape and hard disk have become a lot closer. There are many formats, many of which are proprietary or specific to certain markets like mainframes or a particular brand of personal computer. Tape is a sequential access medium, so even though access times may be poor, the rate of continuously writing or reading data can actually be very fast. Some new tape drives are even faster than modern hard disks. Hard disk. The capacity-to-price ratio of hard disk has been rapidly improving for many years. This is making it more competitive with magnetic tape as a bulk storage medium. The main advantages of hard disk storage are low access times, availability, capacity, and ease of use. External disks can be connected via local interfaces like SCSI, USB, FireWire, or SATA, or via longer distance technologies like Ethernet, ISCSI, or Fiber Channel. Some disk-based backup systems, such as virtual tape libraries, support data deduplication, which can dramatically reduce the amount of disk storage capacity consumed by daily and weekly backup data. The main disadvantages of hard disk backups are that they are easily damaged, especially while being transported, and that their stability over periods of years is a relative unknown. Optical storage. Recordable CDs, DVDs, and Blu-ray discs are commonly used with personal computers and generally have low media unit costs. However, the capacities and speeds of these and other optical discs are typically an order of magnitude lower than hard disk or tape. Many optical disc formats are worm type, which makes them useful for archival purposes since the data cannot be changed. The use of an auto-changer or jukebox can make optical disks a feasible option for larger-scale backup systems. Some optical storage systems allow for catalog or data backups without human contact with the disks, allowing for longer data integrity. Solid-state storage, also known as flash memory, thumb drives, USB flash drives, compact flash, smart media, memory stick, secure digital cards, etc. These devices are relatively expensive for their low capacity in comparison to hard disk drives, but are very convenient for backing up relatively low data volumes. A solid-state drive does not contain any movable parts, unlike its magnetic drive counterpart, making it less susceptible to physical damage, and can have huge throughput in the order of 500 MB/s per second to 6 GB/s per second. The capacity offered from SSDs continues to grow and prices are gradually decreasing as they become more common. Remote backup service. As broadband internet access becomes more widespread, remote backup services are gaining in popularity. Backing up via the internet to a remote location can protect against some worst-case scenarios such as fires, floods, or earthquakes, which would destroy any backups in the immediate vicinity along with everything else. There are, however, a number of drawbacks to remote backup services. First, internet connections are usually slower than local data storage devices. Residential broadband is especially problematic as routine backups must use an upstream link that's usually much slower than the downstream link used only occasionally to retrieve a file from backup. This tends to limit the use of such services to relatively small amounts of high-value data. Secondly, users must trust a third-party service provider to maintain the privacy and integrity of their data. Although confidentiality can be assured by encrypting the data before transmission to the backup service with an encryption key known only to the user, ultimately the backup service must itself use one of the above methods, so this could be seen as a more complex way of doing traditional backups. Floppy disk. During the 1980s and early 1990s, many personal, home computer users associated backing up mostly with copying to floppy disks. However, the data capacity of floppy disks failed to catch up with growing demands, rendering them effectively obsolete. Managing the data repository. Regardless of the data repository model, or data storage media used for backups, a balance needs to be struck between accessibility, security and cost. These media management methods are not mutually exclusive and are frequently combined to meet the user's needs. Using online disks for staging data before it is sent to a nearline tape library is a common example. Online backup storage is typically the most accessible type of data storage, which can begin restore in milliseconds of time. A good example is an internal hard disk or a disk array. This type of storage is very convenient and speedy, but is relatively expensive. Online storage is quite vulnerable to being deleted or overwritten, either by accident, by intentional malevolent action, or in the wake of a data-deleting virus payload. Nearline storage is typically less accessible and less expensive than online storage, but still useful for backup data storage. A good example would be a tape library with restore times ranging from seconds to a few minutes. A mechanical device is usually used to move media units from storage into a drive where the data can be read or written. Generally, it has safety properties similar to online storage. Offline storage requires some direct human action to provide access to the storage media. For example, inserting a tape into a tape drive or plugging in a cable. Because the data are not accessible via any computer except during limited periods in which they are written or read back, they are largely immune to a whole class of online backup failure modes. Access time will vary depending on whether the media are on-site or off-site. Off-site data protection. To protect against a disaster or other site-specific problem, many people choose to send backup media to an off-site vault. The vault can be as simple as a system administrator's home office or as sophisticated as a disaster-hardened, temperature-controlled, high-security bunker with facilities for backup media storage. Importantly, a data replica can be off-site but also online. Such a replica has fairly limited value as a backup, and should not be confused with an offline backup. Backup site or disaster recovery center. In the event of a disaster, the data on backup media will not be sufficient to recover. Computer systems onto which the data can be restored and properly configured networks are necessary too. Some organizations have their own data recovery centers that are equipped for this scenario. Other organizations contract this out to a third-party recovery center. Because event.The site is itself a huge investment, backing up is very rarely considered the preferred method of moving data to a event.The site. A more typical way would be remote disk mirroring, which keeps the event.The data as up-to-date as possible.